recording's rolling. It's Friday the 13th of May. And so you guys will tell me that the AP exam went well, which is a good deal. We got a couple weeks of school left, so let's look at let's do some stuff that's not studying for an AP exam, but I can still teach you guys some last week. How many guys are taking stats or taking stats? Oh, okay, next year? Right. Okay, so I'm gonna give you guys a crash course, try to fit this in like 20 minutes. We're gonna do what we can. So follow along with me. Obviously I'm taking like a whole year's of stuff and trying to fit it to a half hour. We're gonna do what we can here. All right, so first deal, suppose you have a different population. So you guys see 5 dogs, 5 people, and 5 trees. Oh, I meant to mention too, I'm not going to pick this up for a grade. This is just follow along, just learn. It'll be a good time. All right, so do you guys see 5 dogs, 5 people, and 5 trees? All right, now I wonder if we could somehow like analyze this data one way or another. We're going to look at here, folks, here, 2 metrics. 2 metrics on this first page. One is mean average, which is probably something you guys have done for like many years, right? You guys take a mean, just add them up and divide by, well, 5 in this case, because it's like 5 dogs. Right? But also, let's measure the spread of the data, which is something called standard deviation. That's a way to quantify this, right? So here, glance at these numbers. Do you guys see 5 dog heights, 5 people heights, and 5 tree heights, right? Now, let's say that these are, I don't know, like from some particular sample. Like the trees, you guys see how all the trees are like almost the same size? Maybe these trees have been selected for, like, we got to sell some Christmas trees. So we ordered like a bunch of trees from the hardware store, and they'll have to be about the same height because they have to fit people's houses level, right? So each of these samples aligns with one of these curves. Do you guys see a height versus, sorry, a frequency versus height set of axes, right? So increasing height would be going to the right, right? And if there's more of them, well, that'll be like more frequent. You guys, here, go and do this, and then as the story unrolls, you'll see that this will be the case. Label the middle one people. Oh, yeah, okay, yeah, okay, all right. So for video context, I printed off these this morning. All the printers were broken except for one that has a very little ink in it. So yeah, you guys can just draw in the curves. Again, I'm not picking this up. Sorry they didn't print too well. Oh, I did do this though. I did upload these files to Google Classroom. So if you want better versions of these and you want to print them out at home, oh, okay, I see it's a little better. Then you can. The equation's printed out better in the whole deal. All right. So, and you guys remember bar graphs, right? Like bar graphs. So let's say there's somebody of like this height. Let's say, I don't know, 5'7" or something, right? And we've got like so many people. That's like frequency. And then how many people are taller than that? Well, there's some people that are like 5'8", and then 5'9", and then 5'10", but fewer and fewer the taller you get, right? And then how about shorter people? How many people are like 5'5" and 5'4" and 5'3", right? Well, not as many. And then if you aggregate all these bar charts, you can make like what's called a normal distribution bell curve. Well, I'm assuming something called normal distribution, right? But it'll make like this bell curve, won't it? Right? And wouldn't like the average be in the middle, right? And do you guys see a point where, here, do you guys see how like the middle of the curve, it's like an upside down bowl, but the tails are like a right side up bowl? Do you guys see that? And there's a place where it switches. And if you're in calculus, you know the name of that point where it switches. And that's called a what kind of point? Inflection point. I'll call it IP for inflection point. That's right. And there's another one on the other side. And do you guys think that the distance from this mean to that inflection point could be like a measure of how much the data spread out, right? And that's called one standard deviation, which I'm gonna represent with the Greek letter sigma, right? First, lowercase sigma for standard deviation. Okay. All right. Now, how do you let's look big picture before I dig into the equations. Okay. Do you guys see that the people, okay, the heights of people kind of spread out, but dogs, wouldn't it be true that dogs have crazy variation in height compared to people? You get little chihuahuas, you get Great Danes, you get medium dogs, right? And this data also should reflect that, although everybody has individual numbers. So you see the curve on the left, right? The fact that it's to the left means that on average, dogs are shorter than people because anything to the left is lower height, right? But see how it's also more spread out, right? So go ahead and label this dogs, right? Because there's more variation in dogs' height. They have a higher standard deviation among their own population, right? The area under each curve represents the population. Suppose 100%, for example. If it's more spread out, it'll consequently be flatter. So that's a little detail. Okay? And then this last curve, label it trees, and here's why it's trees. Right? the fact that it's skewed to the right means that your trees on average are taller than your people. And you guys see that's true, right? The trees are really tall compared to the people, right? But I made all the trees like almost all the same height, at least this particular sample. That means that there's almost no variability. It means the standard deviation is very small. That's why it's like squeezed in, right? And consequently, because of that, it's also happens to be very tall. This graph is not tall because the trees are tall. The trees are tall means the graph is skewed to the right. Okay, you guys can see that? Is that all right? All right. So how are we going to quantify mean and standard deviation? So you guys know mean. You're just add them up and divide by the number there. Right now, standard deviation is a process. Again, I know your equation didn't print out super well, but let me zoom in so you guys can see it. And I'll walk you guys through this process. So what we're going to do is we're going to take each individual value, that's x sub I, each individual value, subtract the mean. That's what x bar is, like the mean, right, for that group. We're going to, okay, so we're going to bunch of differences. We're going to square those differences. And one thing that squaring does is that you lose all the negative information, kind of like absolute value, sort of, same principle. Then we're going to add all those up. See, if you didn't square it, if you add them up, the sum of the just differences wouldn't necessarily be 0. But square it, ooh, now we've got like some number, right? Then divide by the population size minus 1. So if you have like 5 trees, for example, we're going to do 5 minus 1 is 4. It has to do with degrees of freedom. I'll let your stats teacher explain it to you one day, but I'm giving you guys a crash course today. And then take the square root of that. It's sort of like undoing the square, right? And that's like a whole process of them. You guys see like a whole process there, right? And that is how you can quantify standard deviation. They're using S here. I'm going to use S and sigma interchangeably, although there's technically a small difference, but I'm going to skip through that today too, right? So I've done some math ahead of time. Here's how you take the average, add them up, divide by 5 because we've got population of 5, boom, like so many centimeters. Here's standard deviation, right? So look at that average. It's there, and there. See how I'm subtracting the average, each number from the average, okay? And then square it, and then add them all up. Then divide by the group size minus 1, and then square root it, and you can get a number at the end. Right, you guys get that? Right. All right, now that is a process, but you guys got this model calculator on your desk? Right. I'm going to show you how this model calculator can crunch that whole thing for you. If you don't have this model calculator, I got one here. See a couple of spare ones over there on those desks. So here's what we're going to do. First of all, let's clear out whatever data is there. Hit second, exit stat. Did you guys see this key right here? So second, and then exit stat. You guys see that? Right. And I'll just clear out whatever's there. Okay, so now we're ready to go. So hit second stat. See this button says data above the cosine? So hit second first. So second stat. And it should say one variable. Do you guys see one variable? You guys good? So hit enter. Right. Then hit data. That's really the same key, just without hitting second. Right? Data. You see X1 on your screen? You guys see X1? Right. All right. Then let's plug in these values. So just to save us a little bit of time here, let's just say we're dealing with dogs. I like dogs. Let's deal with dogs. So I've got 85 centimeters for my first dog. Scroll down and see where it says frequency 1. Well, I've only got one of those dogs, so I'm just gonna leave that there. See, if you had if you're a serious statistician, you might have like thousands of dogs. You might have like, I've got 22 dogs under the site, and you type in 22 here. But I've only got one, so maybe leave frequency 1. Guess that. Okay. Then scroll down again. Oh, X2. Hey, that's my second dog. Type in that height. Scroll down, frequency, there's only one of those dogs. Scroll down, X3. Type in my third dog. Scroll down, X4. Type in my fourth dog. Scroll down, type in my fifth dog. You see, I've got 5 dogs, right? That's it. Okay. So I've got the data entered into the calculator. What the calculator is going to do is it's going to run both these equations for me. Okay? You guys can get that? So like this whole process I showed you, like handwritten out, right? It'll crunch that just like in like a fraction of a second. All right. Do you guys see the key that says stat var? You guys see stat var right here? Okay. Click that once you got all your dogs typed in. Okay. And it'll calculate. N is 5. Yep. There's definitely sample size of 5. Right? Scroll to the right. X bar. That's your average. Ooh, average is 100. Hey, looks like I picked up a lucky paper because that looks like, oh, actually, that's exactly what I got here. I should definitely use my later classes too. 101 centimeters average, right? X bar is average. You guys got that? Great. And if you did this right, of course, that should kind of the middle of your numbers. That's what an average is. I'm talking about the mean average, right? The mean. Scroll to the right one more. Now, do you guys see S and sigma? We're just going to use the one that says S. I'm going to use both those symbols interchangeably, but we're just going to use S, right? So I see 16.3. Think of that like a plus or minus factor. That's how you can quantify. Remember, I was telling you guys this right here, the distance from the mean to this inflection point. That is like a measure of the spread variability. That's what that number is. That's like 16 centimeters. Think of that like plus or minus, right? Guess that. So if I start with the mean, well, okay. I know I've got this labeled people, but it could be dogs, right? If I start from the mean of 101 centimeters and I go plus or minus 16 centimeters, see how that covers like most of the curve? Okay, see that? Okay. And I'll get more specific than most, 68%. This is actually 68% of any bell curve is the mean plus or minus 1 standard deviation. In this case, the standard deviation happens to be 16 centimeters. Okay, you guys see that? Sorry. All right. Let me bring up my notes for this. They get the same paper that I have. Yeah, I do have the notes with the same paper and the same numbers. Okay, so there's the mean, there's the standard deviation, and then I could do that for people and for trees and get some numbers, right? That's it. Now take a look at what's happened to the means. 101, 174, 408. So from dogs, people, trees, it's going up. That's why dogs, people, trees goes left, center, right. Okay. And see how the standard deviation 16 to 8 to 4 gets smaller, smaller, smaller. That's why we start with a wide curve for dogs, and then people's like the Goldilocks medium, and then the trees is a real skinny curve, right? You see that? Because not very much variability in those trees. Okay, good so far? Okay, next thing, I've got a new concept for you guys called Z-score. You guys see Z right here is X minus mu over sigma. Okay, sorry, there's a bunch of symbols we're using interchangeably, but here's what this means. This means take an individual can have a Z-score, and a Z-score is a count of the number of standard deviations from the mean, right? And if it's positive, that means greater than average. If it's negative, that means less than average. Walk you guys through this. Okay, so X could be an individual value. Mu could refer to average, or mu and X bar I'm using interchangeably to represent the average. Do you have notes on this written out? Probably buried somewhere in here. Okay, I'm just gonna have to verbalize this today, save you guys some time, right? And then divide by a standard deviation. Okay, so when you divide by standard deviation, what you're effectively doing is you're getting a count of the number of standard deviations that you are from the mean, which is exactly what Z-score is, right? Here, so let's say that you were exactly average, like the average height is, here, we're talking about dogs, right? Let me stick to dogs. Let's say the average dog height is 101 centimeters, and say a particular dog was also 101 centimeters. That would be exactly average, wouldn't it? Oh, yeah. Okay. So if you do 101 minus 101, that would be 0. 0 divided by anything would be 0. So if you have a Z-score of 0, that means you're 0 standard deviations from the mean, which you're exactly on the mean, which means you're average, right? You guys see how that all goes together, right? What if you were, you know, I've got some examples down here. So, actually, I just did this example with you guys. So let's do this example. What if I have a dog that's 68 centimeters tall? Ooh, that's a real short dog, isn't it? In fact, that's a very short dog. So here's what I do in my calculator. I'm just going to follow this. I'm going to do 68 centimeters minus the average of 101, because that's my average dog size, right? Group that in parentheses. Then I'm going to divide by, remember I had a standard deviation of 16.3 centimeters? Right, divide by 16.3. This is going to give me a count of how many standard deviations this dog is from the mean. And it's going to be negative because this dog is shorter than average. I'm getting -2. You guys see -2? Right? That means 2 standard deviations from the mean. That's like to the left, like 2 standard deviations. That put this dog right about, well, pretty far left on the curve. Right? That's it. Right. Right, and we're going to see what to do with it, because there's a piece you could do after this that involves like a Z table. Right? Right. You guys good so far? That's right. All right, so let me do one more dog. Here, let me show you guys. Because what if I have an average 101 plus the 16.3? When they give me a dog of height like 117 centimeters? Okay, let me just show you that 117 centimeters would equate to 1 standard deviation above the mean, which is like this inflection point. So if I start with 117 centimeters, subtract off the average of 101. Okay, so now I've got the fact that the dog is taller than average. Okay, so I know that. I know how much. Right? Then I'm going to divide by the 16 centimeter standard deviation, right? And that gives me, a Z-score of 1 to say this dog is exactly 1 standard deviation above the mean, right? All right, you guys good? Now, my next question might be something like, all right, if you have a Z-score of 1, if you're 1 standard deviation above the mean, where does that put you in the entire population? Okay, all right, you guys ready to flip over to part B? Right. Right, so, do you guys see this normal distribution curve right here, going on right here? Right. Now, there's something in statistics called the 68, 95, 99.7 rule. Right? And that means that if you are plus or minus 1 standard deviation from the mean, that covers 68% of the population. You guys see that? Right. If you're plus or minus 2 standard deviations from the mean, that covers 95% of the population. And if you're plus or minus 3 standard deviations from the mean, that covers 99.7% of the entire population, right? So no, I'm using height as an example for some metric, but you could do any metric, right? Bell curves are all over the place in nature, right? And there's individual variability. And if you have a Z-score on any metric that's like 3 or more, that's a crazy high Z-score. That means you're like well within the top 1% on that particular metric. Could be height for my example, whatever metric you want to look at. Do you guys see some numbers underneath this curve go from -3 to 3? You guys see these 7 integers? Those are Z-scores, right? They count the number of standard deviations left to right. You guys agree with that? These concepts so far? All right. So yeah, let's take this to the, well, yeah. Here's what we do. You guys got any questions so far? Okay. All right, so suppose you ran your numbers, right? So I got some bottles here filled with some water, right? I'll attach a story to this. Okay? Let's say there's a machine at some factory that's filling up bottles with water. It looks like they're supposed to be 1 liter bottles, right? Because they're all hovering about 1 liter on my paper anyway. Okay? But some are a tiny bit more, and some are maybe there's this one got a little bit less there, right? But maybe this machine isn't perfect, right? It's got a little bit of variability. Might be like a normal distribution, right? And let's say you're like some government official at let's say a consumer protection agency, and you want to figure out, is there truth in advertising? They're advertising 1 liter. And let's say there's some rule on the books that says, well, as long as like 95% of the bottles are like more than 1 liter, then we're good to go. And we'll consider that like good enough for the standard, right? So you grab some bottles off the shelf. Let's say you grab these bottles, right? You do that number crunching I just showed you guys how to do, and you get like this average and this standard deviation, right? Like, okay. Yeah, thank you. So then, now hold on to that story. That's going to come back, especially with the next part we're going to look at. Right? Let's say you grab a 7th bottle off your shelf. Also, if you guys want to run the numbers, I did a unit conversion here too. You guys see liters here and milliliters here, so just something to keep your eye on. Right? Let's say you go back to the store and you grab a 7th bottle. It's like this many milliliters. You're wondering, I wonder in the big scheme of things, where does this bottle fit in among all the other bottles? Right? Is it? And I do see that this particular bottle has less liquid than the other bottles, right? But how much less? Right? So I can check its Z-score. So I run the Z, right? So I have information about the mean and the average from these bottles. Now, this is a really small sample size. So it's not very realistic, but we're just going to make some abstractions here, some simplifications, right? So I get the Z-score for this particular individual bottle, right? Its own value minus the average divided by the standard deviation, right? And I'm getting a Z-score of like -1. Now, for this particular paper, everybody's got different numbers, but I did make all these come out to integer values. So it's got to be one of these 7 numbers. It's from -3 to 3, but it's an integer. Mine is really close to -1, so I'll call it -1, right? And then the question, here's sort of new territory, is what percentage of bottles contain less liquid than this bottle? Okay, so if you have a Z-score of -1, right? So Z-score -1, then look right here. Would it be true that the left tail represents all the bottles that have less liquid? And these all add up to 16%. If you add them up, they add up to 16%. Okay, so the answer is 16%. Right? If you have a Z-score of 0, the answer would be 50%, because 50% of the bell curve is to the left. If you have a Z-score of +1, the answer is 84%, because you have more than 84% of the population. Okay. If you have a Z-score of +2, well, what is 84 plus 13.5? That would be like 97.5, right? Be like in the top like 3%. Yeah. You guys get that? Okay. All right, you guys ready for stats part C? Stats part C? Okay. Actually, let me lead in right before we do that. Let's look at this table on the back. You guys see this big old Z table on the back? Okay, I'm gonna show you guys how to read and interpret this, right? Because this is really powerful table. Okay. It should have told you guys before I started this whole thing. There's a couple of reasons that I'm giving you guys a crash course on stats today, right? One reason is that these are all new concepts. This gives you like a new model to work with. This could be a really powerful tool that you could use in all different fields of science, like biology or economics or all over the place. You deal with like probabilities. Okay? And also, I want to give you guys a crash course on stats sometime next, or sorry, quantum mechanics sometime next week. I'll give you guys like a short version, but quantum mechanics, things exist probabilistically. So it's also really helpful, really nice to have this model in your mind, right? So I'm giving you guys all new concepts, right? All right, so the Z table is in two halves. It's all part of the same table, it's just two halves. The left half is less than average, which has all negative Z scores. So you guys see the leftmost column has Z and see it's all negative Z scores. And it goes up to 0. Right? And the right half is anything that's more than average, which starts at 0 and turns into positive Z scores. That means you're like above average, right? You guys get it? It only goes up to positive 3.49 because you get more granular the further to the right you go. So here's how you read this. So I got a Z score of, let's see the highest Z score you could possibly get according to this, well, that's available on this table, I should say, right? And so you guys see it goes to 3.4 down here, but then you got 3.40, 3.41, 3.42. And as you go to the right, you get more granular. See across the top, you can go to 0.09. You see that? Okay, so this very last cell on this whole table correlates to a Z score of 3.49, right? Which is pretty well approaching 3.5, right? And what numbers are actually in this table? If I zoom in, see it says like 0.9998, right? That refers to the amount of the bell curve that's shaded up to that particular Z score, right? And 0.9998, that refers to 99.98% of the entire population, right? So yeah, if you have a Z-score of 3.5 on some particular metric, that means that you are like within the 0.1% like top of that population, right? Right? You guys get that? Okay. Talking about like how much the bell curve is shaded into the left, right? You guys follow that? Okay. In fact, this is a more exact version of what this could tell you with integer values of Z. So what we were looking at before with this bell curve broken up in these just a handful of intervals, right? This is a simplified version of this more precise Z table, right? Is that? Okay. All right, so there's one last new concept I want to throw at you guys. Right, and that is if you start putting things in groups. Let's go back to that story of you're a government official working for a consumer protection agency, right? And maybe you want to check, see the volume of water in a bottle, see is it straight an advertisement, or another specific example I remember is suppose you're running a peanut butter factory. Do you guys think that lots of insects are attracted to that peanut butter? Yeah, do you think there's probably some insect parts inside your peanut butter when you buy it? Yeah, it's a thing. It's back to life. But what the government will do is they'll put a regulation on it and say, well, you can't have more than so many insect parts per million, right? So something like that. Right? And so you can do statistical analysis and then follow the whole deal. But I'm giving you guys that particular story because that's very closely aligned with what I'm about to show you guys right here, which is your government official, you grab a bunch of peanut butter jars off the shelf and you try to get some kind of indication of what that means for like the entire like sale of peanut butter sold like nationwide, right? So we're going to use height though. We're going to use because we've been using that as an example. So we got mean, standard deviation, Z-score. We've gone over all those. But one more thing, what's the Z-score for like a group? And Z-score for a group goes like this. It's Z-score for I didn't mean Z-score, I meant standard deviation. Standard deviation for a group. It's what it is for an individual divided by the square root of the group size. Right? So what's that about? What's that used for? Right, so I'll take you guys through the story. Suppose that the average human height is, my paper says 180 centimeters. Let's just run with it, right? And the standard deviation is 12 centimeters. Remember, that's sort of a plus or minus factor. So what we've gone over so far is that 180 centimeters plus or minus 12 centimeters should cover 68% of the population. Then you got some super tall people and some super short people, right? You guys get that? Right, so first two questions. What's next person that walks through that door right there? What's the expected height, right? Well, I don't know. Could be anybody. So if money's on the table, may as well guess the average, right? Some taller, some shorter. Let's go copy paste this number, right? You guys get that? Right. What's the standard deviation? Like that plus or minus factor. Just copy paste that number. Now again, that's for a single individual walking through that door. And then you could ask things like, well, what's the percent chance that somebody who's 190 centimeters or taller walks through the door? Now at that point, wouldn't we be talking about effectively like this white tail on this bell curve, right? If the average is 180, we're looking for 190 or taller, wouldn't you be finding like this tail of this curve, right? And we could do that, just find a Z-score, navigate that that table. And here's the numbers I got. I got a Z-score of 0.83, right? and therefore the right tail would come out to 20%. Right. So there's only 20% chance they would be like this tall or taller. Right. You guys got that? Okay. Right. Now here's the thing though, is what if you started putting people in groups? What if there was a group of 5 people that walked in through that door, right? And you said, what's the percent chance that the average of that group of 5 people is 190 centimeters or taller? Ooh, would that be probably a very small chance? It would have to be less than 20%, wouldn't it? Because now we're talking about a whole group of people. In fact, if the entire world, like 7 billion people walk through the door, that chance would approach 0. And it would necessarily be that the average height of the whole population of people is necessarily the average, right? You guys get that? Right. So what we're going to do is the average height of a group of people is still what it is for an individual. So that this is the same number, right? But the standard deviation, now you're going to divide by the square root of the group size. So I've got a group of 5 people, so I'm getting this. You see how it's a smaller standard deviation, right? Because now, now the group size is going to necessarily approach the mean. There's going to be less variability because it's like a whole group, right? Right. So now what's the chance that the group of people is 190 centimeters or taller, right? So run the z-score now with this new smaller standard deviation. It's a higher z-score. Ooh, notice the z-score went up, right? It more than doubled, which means that the percent chance that this is going to happen is now getting very, very small, right? For an individual, 20%, but for a whole group of people to all be super tall, right? That's in single digits, right? You guys see that, right? Now, I told you guys that one of the reasons I'm showing you guys stats is because this is a good intro to like quantum mechanics. Part of quantum mechanics is particle physics. So like all these elementary particles people discover, like scientists are discovering it, like for example, over the Large Hadron Collider. Right? Okay, we got protons and neutrons and electrons, great, right? But they also find all these other type particles. For example, famously, the last one that was discovered 10 years ago was something called the Higgs boson. But how do they discover these things? Because you can't take pictures of these things. We're talking about elementary particles, right? So they have these particle collisions, and they're analyzing collision results for mass, charge, and spin. And they're getting all this crazy statistical data. And what they're doing is crunching this data and saying that these particles have to exist, because if they did not, then you wouldn't see this particular outcome of this data. But it's all statistical. You have to run like billions of collisions to even see if this is the case. I've heard an analogy of discovering a particle this way. It's kind of like rolling a grand piano down the stairs and listening very carefully to the tinkling of the keys and figuring out, oh, well, you must have had a piano that originally looked like this and had the keys this way, so that it sounds like this crash sound as it's going downstairs. Okay, so but you have a group of 5 people that walk through the door that's regularly like super tall, right? If by random chance that should only happen very rarely, but it's happening more often than it should, then you might start to hypothesize like, there might be some reason that groups of 5 very tall people are walking together. Ooh, you know what? We've got this model over here that hypothesizes the existence of this sport called basketball, where there would necessarily be groups of 5 like very tall people. And then if you got the percent chance, like empirically, it comes out to like, oh, now there's like a 10% chance you'll see groups of very tall people. Or what if it's not 3? What if it's like 3.5? It's like, there's something amiss here. Well, the only way for that to happen is if like some phenomenon exists like basketball. So you have basketball teams, and that's sort of analogous to like a Higgs boson particle existing, right? Whew. All right, so I did fit that in all in time. Wasn't sure if I was going to, but it happens. Right. You guys got any questions about stats? Okay. All right, so here's what we'll do officially is go back to this page. You guys see like your height and the heights of all your friends. Right. So I'll give you guys the last few minutes of class. You guys can take some meter sticks and find each other's heights and crunch some numbers and see where you fit among all your friends. See if you're tall or short. And we'll call that a wrap on today.